Okay, hello everybody on YouTube. I'm just going to be doing a live stream this afternoon. It's currently Friday. I've just been teaching in school this morning, doing some stuff for OCR, so some sort of kind of paper 1 revision. But this stream is very much based on AQA paper 1. Okay, and what I want to do is, first of all, for anybody watching the kind of recap of this, what I'm going to be doing is going through predicted paper 1, and also I want to tell you about two things. Now, the first one is I'm going to be running some masterclasses this weekend. Saturday morning I'm doing AQA paper 1 revision. Saturday afternoon I'm doing OCR paper 1 revision for modelling physics, and then on Sunday I'm going to be doing AQA paper 1 revision in the morning, and then I'm going to be doing Edexcel paper 1 advanced physics paper 1 on Sunday afternoon. Now, if you want to book anything, I've got this big red banner here, and basically you can go to my website, which is alevelphysicsonline.com. You can go there, you can book your place on a masterclass. I only have a limited number, and obviously the bookings are going to close quite soon, especially for the one tomorrow. The other thing I'd like to say is that although this is a predicted paper, I don't think that these questions are necessarily going to come up this year, but I do think that they're a good source of additional questions for you to have a go at. Now, at this point, I guess we've only got less than a week to go. Most of you will have done most of the past papers from 2024 all the way back to 2017, and you're going to start to run out of questions. And so I'm going to talk about some predicted papers, and the ones I've got are from PMT. A lot of you might have seen these and have downloaded them already, but PMT for AQA only have a paper 1 and a paper 2. And so what I've got here is my own paper. This one is for paper 3A, and I've got 3 versions of this. This one here is a practice paper of the type of questions that you could get asked about in your exam. So I would say that if you want to find the type of questions which took a long time to actually write and put together, I do have practice papers. I've called them alpha, beta and gamma just to distinguish them. They come with the whole question paper, so that took a long time to produce. Of course, I have a mark scheme for you to quickly and easily mark your answers, and also I have model solutions that you can download as well. And basically this is a load of my work solutions to actually how to approach that. So if you need to have practice papers for paper 3A for AQA, you can buy these, and there's a link in the description beneath this video in the live stream where you can go to my shop and download them. Basically, you can download them today. It's only £9.99 for all 3 papers, and there's a lot of stuff there. Now, the thing I'm going to be going through today is this thing here. So this is the PMT education one. It's a free download. I think it's a great bit of marketing because everybody's talking about this. I've had lots of students asking me about this, saying, should I do it? I've had teachers saying, do you reckon it's a good thing? And I reckon that this is a good source of questions, but I think by going through it kind of step by step, there's a few things I'd like to clarify. And I did this just because I think, well, first of all, the word prediction is in the title of this live stream, which is why you're watching it now. And this question paper has lots of good practice questions, but I have no idea if these are going to come up in the exam. But because I personally feel it's impossible to predict what's going to come up. And what I've done over the last year is lots and lots and lots of past papers. In actual fact, if I go over to my website, so this is A-Level Physics Online, if you go to the front page, you can either kind of click on the link up here, you can click on more where it says past papers, or you could even just go to maybe the AQA page, and then when you see the past paper and work solution thing, I've got a big past paper finder. Okay, now within this past paper finder you can find any past paper, mark scheme, examiner's report and other things as well. So let me just show you what I mean there. So you can find, and you can like filter by exam board. So you wanted to look at AQA, you can look at AQA A-level, and maybe just want to look at AQA A-level paper 1. You'll see I've got all of the exams reports here in an easy to find place, and also I've got my work solutions and video work throughs as well. In actual fact, looking at AQA in particular, if I just click on the videos with work solutions and the full video walkthrough, you can see I've got all of the AQA papers from 22 and 23. So I've got paper 1, paper 2, paper 3A. I've got the Astro, I've got medical, I've got on the next page, I've got engineering, and also I've got turning points. So I've got a huge amount of papers there, and actually if you look at all of the exam boards, you can actually find there's a huge amount of video workthroughs that you can find on my website. So you can find all of that at A-Level Physics Online as you're working through stuff in the coming weeks. Okay, but this one here is an AQA paper that I'm going to be going through today. So the first part looks just like a normal kind of AQA paper. Then we have the tutor. I don't know her actually, but I have worked doing some stuff with PMT in the past, and I think a lot of you might have seen actually, if you go to PMT, there are work solutions to the AQA multiple choice questions by topic that I work through my answers with. Maybe that gave them the idea to do this, potentially, so there's some kind of work solutions. But basically, I don't have any kind of business interest in PMT. I just think that this is another source of questions that a lot of you are going to be working through. And obviously, it's a really good lead magnet. PMT have done this because they know that everybody's going to download these predicted papers. They're going to see their adverts and so on. Right, so what I have here is a question. I've got the model solutions that we can refer to if we need to. And also I've got the mark scheme. So I was going to go through this sort of step by step. And also when I contacted PMT the other day, I said to Gorkum, can I do this? And he said, yeah, not a problem. So obviously a lot of you might have seen this. This first question, again, I don't think this is necessarily a prediction, but I definitely think that this is a style of question they will ask. They often have the first question being about particle physics. And for those of you who haven't already done so, I do have a load of flashcards that you can download in my online shop. So I've got a load of flashcards that you can basically download and print out and use these as you're revising. So they've all got the kind of the key things about this module. When you buy them, if you want to get them, it's a free download. You can basically download about 55 of what I think are the most important key terms in this first module, and you can use that just to learn things. Okay, so for example, we've got the quarks and mesons, and we know that a pion is maybe an up-down, a neutral pion is up anti-up, a pion which has got a negative thing is a down anti-up. So these things here are just things that you need to know. So given that the particle X has a strangeness of -1, deduce its quark structure. So this relies on the fact that if you've got a pion, then the structure of this will either be up anti-up, or it'll be down anti-down. Okay, it's a baryon with a quark structure of up, strange, strange. So what I would say is for something like this, I don't know how to actually draw that symbol. Is it something a bit like this? Whatever it is, it's going to be a random thing. This makes X, and it makes this neutral pion. Now, I'm going to think about Q, B, and L. Okay, the charge on that is going to be 0, and therefore this thing here, the charge is going to be 0. The charge on X is also going to be 0. The charge on the pion is going to be 0 as well, so we've conserved charge. In terms of what else we have, it says this thing is a baryon, so whatever we start with, it's got a baryon number of 1. The pion, because it's a quark-antiquark pair, it's not a baryon, so it's going to have a number of 0. But in order to conserve baryon number, this must have a baryon number of 1. And of course, neither of this, or this is a lepton. So again, we conserve lepton number. So we must have a baryon, and therefore X must be made out of 3 quarks. Now it says as well that this starts with a quark structure of up, strange, strange. We know that this is going to be the up anti-up, or it could be a down anti-down. And of course the pion is just one of these kind of bosons which can be used to exchange a force. So it says particle X has a strangeness of -1. That then I guess leads us back to what we know about the strange quark. And looking at the data that you're given, you're told that a strange quark has got a strangeness of -1. Okay, now if this particle X has got a strangeness of -1, then that must mean there's only one strange quark inside it. Whereas previously we had something with two strange quarks, so that would have a charge of -2. So now what we've done is we've not conserved strangeness. Okay. Instead though, what must have happened is that one of the other strange quarks must have decayed into this. Okay, and I guess what we're going to have is something which is up, down, and estranged. Now, I guess the way we might think about that is that because it's a baryon, these must all be quarks. There can't be any anti-quarks in this. We can also think that this thing must have zero charge. And if we know that a strange quark, and you're given this data in your actual data sheet, a strange quark has got a charge of -1/3. We know that an up quark has got a charge of +2/3, and a down quark has got a charge of -1/3. If you've got a strange quark in this, then whatever else we have, this plus that must be equal to 1/3 in order for there to be no charge. So it has to be UDS. If it was down, down strange, then we'd have a charge of -1. If it was up, up strange, then it would have a charge of +1. And so the only combination of quarks that we have that can actually give it a charge of 0 must be up, down strange. Now, for this, you don't need to remember that, but what you need to think about is that any time you've got one of these particle interactions, we always conserve the charge, baryon number, and lepton number. So this is how we've deduced its quark structure. So basically we've looked at, and I think what's the mark scheme say? It says we've looked at the kind of conservation law, so we'd get a couple of marks for this. And therefore I think it would be also super important to therefore say UDS, make it nice and clear, underline it, and that's going to be our final answer. State and explain which interaction is involved in this decay. So what we've got here is something where strangeness is not conserved, and therefore it's the weak interaction. So that's going to be the first point, which is state. So I'm just going to highlight that. Okay, so weak interaction is going to be the first mark, and the explanation is because strangeness is not conserved. If strangeness had been conserved, then this would be a strong interaction. Okay. Okay, somebody says, DS says, also check out my revision videos for the AS portion of paper 1. Yeah, basically, I've got lots and lots of stuff over A-level physics online. You can basically find all of that by going to A-level physics online, and then everything is there that you need. I'd say that one maybe criticism I've got is the word deduce, because I haven't really seen the word deduce as a command word. But I think the first one here about state and explain, they're kind of legitimate command words. So there we go, we've got the first few marks already. My gosh, this stream, it's going to take hours, isn't it? Right, in a different decay, the particle, whatever that is, lambda naught, decays to a neutron and a neutral pion as shown. State the quark structure of this particle here. So the first one, it's just actually a really simple question, so maybe it should have been the very first one. What is the structure of a neutron? So a neutron is just going to be up, down, down. So that's something that you just need to remember. Clearly stated in the specification that you must be able to recall the structure of a neutron. And again, I think I have this on my set of cards here. There we go. So a neutron, if we look at that, it says a quark structure is up, down, down. So just some of these facts that you need to just remember. Right, the next question, I'll give myself a tick for that. How's everybody doing, by the way? Friday afternoon, lovely and sunny. If you're here, then that's amazing. It says, the neutron is not stable and will decay after approximately 10 minutes. State what particle or particles it will decay into. and then deduce all particles released. So what else would we be getting? So this one here is an easy question, and you have to remember about the decay of the neutron. So a neutron decays into a proton plus an electron plus an anti-electron neutrino. Okay, now I would have said state the particle it decays into. I guess this isn't maybe the same style as a real exam question, but I would say that if you think about the charge, the baryon number and the lepton number, we've got a charge of 0, plus 1, minus 1 and 0. The baryon number is 1, 1, 0 and 0. And then we have a lepton number of 0, 0, plus 1 and minus 1. So I guess this is the way that this question says to deduce that. But basically this is just a fact that you should be able to recall. So a neutron will decay into a proton, an electron and an anti-electron neutrino. So there we go, just some more facts that all of you need to know. Now again, this isn't maybe the same as a real exam question. What's the mark scheme say for this one? It says, it just says basically, yeah, a neutron to a proton, beta minus 1 electron and an anti-electron neutrino, 1 mark for correct equation, 2 more marks for conservation rules. I guess I'll just give myself a couple of marks there. So that one there is just something that you just have to remember. Right. A typical raindrop has a mass of 4.19 milligrams. When falling, it quickly reaches the terminal velocity. Draw all forces acting on the raindrop and determine their magnitude. So my approach to this would be you have to use a ruler, and also you have to use, I think, a pencil. Okay. Is it compulsory to write an anti-neutrino? Yes, it is, Daya. You have to write the anti-neutrino, otherwise we wouldn't conserve the electron lepton number. Yeah. Right, so what I'm going to do is I'm just going to put a dot in the middle of this, and that's going to show where the two arrows come from. Now I reckon I want to get a nice large arrow. I'm going to make it vertical. I'm going to go from 0 up here to 5 in the middle, down to 10. Okay, and the key thing here is I've tried to show that I'm basically drawing these arrows from a central point, and that means the arrow up is going to be equal in size to the arrow down. Now, pencils used in case I make a mistake with this diagram. Of course, you can go over it afterwards in black pen. So draw all the forces and determine their magnitude. So if it's falling, it's going to terminal velocity. So we've got the weight force acting down, and then we've got the drag force due to the air resistance acting up. Okay, their magnitude, well, the weight force is going to be equal to its mass times the gravitational field strength, which is 4.19 times 10 to the minus 3 kilograms, sorry. No, that's milligrams, so that's going to be times 10. I haven't actually done these questions yet, so I'm just hoping I'm right. So it's 4.19 times 10 to the minus 6 kilograms. And then we're going to multiply that by 9.81, the acceleration due to gravity. So this gives us 4.11 times 10 to the minus 5 newtons. Okay, how's that looking? Let me have a quick check of what they did over here. Yeah, so basically I'm going to put that as 4.11 times 10 to the minus 5 newtons, and then the drag force is also equal to 4.11 times 10 to the minus 5 newtons because it's acting in the other direction. Let's have a look at what they did here. Will you need a protractor? Yes, please make sure you have a protractor. A protractor doesn't cost you much. I did a question last night in my edXL thing where we were looking at some vector diagrams where you needed a protractor to measure some angles, and I think a protractor is super important. So yeah, you definitely need one. Right, the model solutions, let's see what they've got. The model solutions say, okay, they've got drag and weight, they've got the same thing, but I think it's maybe not so clear on here that they've actually got two arrows that are the same size. So I think that's why it's really important to actually put the dot in the middle to show that the size of the arrows is the same. We've determined the magnitude. You don't need to say why that is, because it says it's terminal velocity. You don't need to explain why they're the same size. Okay, that first bit, not so bad. Air resistance acting on the raindrop can be calculated like this, where you've got the drag coefficient, the density. Now, you do not need to know that equation, but this is an example of where you've got an exam question where they will give you an unknown equation, and then you've got to use this alongside your current knowledge to actually work something out. Okay, somebody says, this is a great question. So we've got, is that Eric? Right. This paper's easier than previous years from AQA. Yeah, I think the last couple of years of questions from AQA have been a little bit more tricky. I suspect because they've been so tricky, they've really had to analyse what they're giving to students this year. So I predict that the 2025 papers won't be as hard as the 2024 or 2023. I'd say maybe a bit more tricky than this predicted paper, but these questions are relatively straightforward. Okay, so we've got all of this stuff here. A is the cross-sectional area of the raindrop, hence determines typical cross-section area of a raindrop travelling at terminal velocity. So we know that the size of this drag force is what we worked out over here, which is equal to the weight. And so we can basically say that the force due to the air is equal to the weight force of that thing. And therefore, if you know the weight, mg, that's going to be equal to a half cd times the density of air times the cross-sectional area times v squared. And we want to find the value of A. So A is going to be equal to 2 times the mass times the gravitational field strength divided by the drag coefficient times the density of air times v squared. So that's just going to be 2 times 4.19 milligrams, that's times 10 to the minus 6 times 9.81 divided by 0.47 times 1.20 times the terminal velocity, which it said here was 9 meters per second. And I'm basically writing everything here as we've been given it, squared. So bear with me while I do this. The reason that the force is equal to the weight dia is that we've got something that's falling at terminal velocity, so there's no resultant force because it's not accelerating, it's travelling at a constant velocity. So I've got an answer of 1.799948, so I'm going to say that's equal to 1.8 times 10 to the minus 6 meters squared. Okay, is that right? I mean, it looks like a very, very small number, but we're going to have a very small number because the area of a droplet is going to be very small compared to a square metre. I've given my answer to 2 significant figures because we've got 2 significant figures up here, and that's going to be my limiting case of that. So I think the answer they've got here is 1.80. Again, I'm just going to see what PMT have put here. They've given it as 1.80, which is fine, but I've given it as 1.8 because that's the least number of significant figures in that raw data. By modelling the raindrop as a sphere of uniform density, show that the cross-sectional area of the raindrop can be given by A as pi 3m over 4 pi rho to the 2/3. So a question like this, is it Dia? Okay, sorry. Right. Has AQA ever asked for any derivations like for diffraction gratings or Young's double slit? I've not seen a question where they've asked you to derive that, but it says in the specification that you must be able to derive the equation for a diffraction grating, so therefore you must know how to derive it, definitely. Just as an aside, should we have a look at that? So if you want to find the derivation for Young's double slit, if you go to A-Level Physics Online, you go to the main page. If you go to the bottom of the page, it says down here, oh, that's weird, it's gone. Let me just refresh that. So for AQA, there should be, oh, there it is. On the main AQA page, it says derivations. If you click on that, you can then see all the derivations that you might need to know, and one of them is d sine theta, and so I've got the way that you can derive this from sort of first principles, looking at the path difference, relating that to the path difference here, and relating that side to this side, and then that angle there. So that's basically the way to do it. And if you want to go through that in more detail, I will be doing that in my masterclass this weekend, which will be coming up quite soon. Okay, so the first thing to do is to draw a diagram. So that is my sphere, and what we're going to look at is how that's related to the area. Okay, so maybe this is like a 3D version. I'm just going to add a bit of shading for the sake of this video to show that basically this is our sphere, and this is going to be the kind of sort of the cross-sectional area. So what do we know? We know that the volume of a sphere is equal to 4/3 pi r cubed, and the area is equal to the area is just pi r squared. Okay, because we're just looking at the cross-sectional area of that spherical object. So I guess we can of course relate the two things together. It says here that by modelling it, show that the cross-sectional area is given by this. I guess that volume here is going to be related to the mass and the density, because the volume is just equal to the mass divided by, or the density is equal to the mass per unit volume. So the volume is the mass per unit density. So we could also write this as m over rho is equal to 4/3 pi r cubed. I guess of course we could take this and say that because the area is pi r squared, we could basically say then here that r is equal to 3m over 4 pi rho, and then it's going to be the cubed root of that. So that's basically all of this to a third. Okay, and then of course we could replace this r squared with this thing here squared. So the area is going to be equal to pi times r squared, which is going to be 3m over 4 pi rho to a third squared. So that's going to be to the 2/3. Does that make sense? Okay. This stream, by the way, will be posted as a live stream on YouTube, so you can catch up and forward to the question that you need. But I just thought I'd spend the afternoon working through it. I don't know if anybody's watching. There seem to be a few people in the chat, which is great. So there you go. That one there, I'd say that again, it's hard to kind of work out where this fits, but I guess we're going to start from this. We're going to start from this. We're going to get to this, and then we'll have something to show that's the right answer. So that would be my approach. A student calculates the distance travelled by the raindrop before reaching terminal velocity using the equations of motion. They argue that the initial velocity of the raindrop is 0 and the final velocity is 6 using a equals 9.81. Explain whether the student is correct, justify your answer. Well, basically, if they're using the equations of motion, these are often Suvat equations, that's how they're called. And for a Suvat equation, A is going to be uniform. But we're not going to have a uniform acceleration because as it gets faster, the drag force increases. So for this, let's have a look. What's the mark scheme say? Yeah, I would say, sorry, 1 second. I'd say, explain whether the student is correct. I would say they are incorrect. I guess you then need to say that Suvat only applies to uniform acceleration. And I guess in this case, as a droplet gets quicker, the resultant force is going to depend upon a function of the velocity of that thing. So as it gets quicker, the drag force gets bigger, so the resultant force gets smaller. And I guess you can say here that the acceleration of, with a capital letter of course, acceleration of the droplet decreases as it increases velocity. And I guess you could then explain how that's related to the resultant force acting on it. So I guess you're going to get something here for stating if they're correct or not, and then a couple of marks for really justifying your answer. But I don't want to do too much writing. Okay, somebody says, why is pi r squared the cross section of that raindrop? Let me just get a piece of blue tack. So imagine this piece of blue tack is the raindrop. Now obviously we've worked out the volume because it's 4/3 pi r cubed, but as it's falling towards the ground, if you look at it end on, it looks like a circle, and therefore for this object here, which is a sphere, the cross-sectional area is still a circle, so that area is pi r squared. And I guess if I held this head on, you couldn't tell if it was actually a cylinder or if it was a sphere if you look at it head on, because both a cylinder and a sphere and a cone all have a cross-sectional kind of frontal area. Okay, and it's just that pi r squared that we're looking at. Okay, but that's good. And by the way, Anthony and other people there, great up to hear kind of people explaining things in the chat. Okay, right. The same student thinks that the mass of the raindrop increases, then its terminal velocity will decrease. Explain whether the student is incorrect, or correct, I guess. So, let's think back to what we had. If we've got this droplet, then the weight force, which equals mg, is going to be equal to the drag force, which we said on the other page was equal to a half c, the kind of the coefficient of drag times the density of air times the area times v squared. Okay, so basically what this says then is that if the two things are equated, the mass is going to be proportional to this force, which is proportional to the area. Is that right? Okay, so I guess we can say here that v squared is equal to mg over a half cd, density of air, times area. Okay, so the velocity is proportional to the mass and inversely proportional to the area for the terminal velocity. Now, how's the area related to the mass? I guess we saw as well in that last question that I've just thrown it away. We can also see from the last question that the area is proportional to the mass to the 2/3. So the area is proportional to the mass of that droplet to the 2/3. And therefore I guess we could put this into there to say that the terminal velocity is proportional to the mass divided by the mass to the 2/3, which I guess then is equal to mass to the 1, take away mass to the 2, so that's basically proportional to mass to 1/3. So basically the terminal velocity is proportional to the cube root of the mass. So the student thinks that if the mass of the raindrop increases, then its terminal velocity will decrease. Actually, if you increase the mass, then we increase the terminal velocity. So I would say, yeah, so basically you increase the mass, you increase terminal velocity. Okay, how does that look? Now, can I go through the question again? Yeah, so somebody says, you know how earlier you had an examiner on, and they said that the mark scheme is amended with suitable solutions added to, if they seem sensible. Yeah. So, basically, by the time you see the uploaded mark scheme, that's the thing that's gone through the various iterations, that basically they write the first mark scheme, they have an examiner's thing, and I say here that because the terminal velocity is proportional to the cube root of the mass, I would say that's the right answer. What's the mark scheme say? Okay, here they said that the mass is proportional to the velocity squared, because they've not accounted for the fact that as you increase the mass, we also increase the area. So I think that's incorrect. The last statement's correct. The first one is a correct statement, but I think they've made a mistake here, because when you increase the mass, you also increase the area, which hasn't been accounted for, saying that mass is proportional to v squared. So I don't think that's correct. So what they would do if they saw something like this, if the real examiners were marking something, they'd realise what the right answer is, and therefore that would then go on to an amended mark scheme, which by the time it gets published is going to be the final mark scheme. Okay. Okay, sorry, JJFO4, you helped make the model solutions to these. No, wait. Okay, hello. Yeah, the area would be constant, but the thing is, it says up here in the question, if you're increasing the mass of the raindrop. Now, if you're increasing the mass and it's still made out of rainwater, the density is going to remain the same. So if you've got 2 raindrops of mass m, maybe m1 and m2, if you were to double the mass, we must have a bigger area for that mass to fit in. So that's, I guess, yeah. Yeah. Okay, so JJFO4, is that really you? If that's really you, that's amazing. And by the way, yeah, this is like a minor thing. It's a difficult question, so I'm not trying to criticise too much. I'm just saying that this would be my approach. But yeah, send me an email at hello@physicsonline.com. It'd be great to hear from you. Yeah, so I would say that would be my answer, because they've not accounted for the area. So what I did really, the first bit here goes back to the first part of the question where we had to draw something at terminal velocity. The weight force is equal to the drag force, which is how we got to this thing over here to say that how v squared is related to these two things. Oh, actually, have I made a mistake? Oh no, actually v squared, okay, I've made a mistake here. V squared is proportional to mass over area. So v squared is proportional. So v squared is proportional to m to the third. So I guess, yeah, basically what we're saying here then is if v squared is proportional to the cube root of m, it still means as you increase the mass, the velocity goes up. Okay, as somebody, Cheese, great name, just said, yeah, so basically, should I write this out again? I'm going to do it again so it's a bit clearer. This is a bit that hopefully you can kind of skip forward in the thing. So basically, the weight force down is equal to mg, and the drag force up is equal to a half CD rho air area times velocity squared. So that means we can say that the mass down mg is equal to a half times that coefficient times the density of air times the area times v squared. And that means that v squared is equal to mg over, or 2mg, over the drag coefficient times density of air times the area. And provided you've got the same gravitational field, the same type of shape, the same density, and that number 2 is the same, we can say that v squared is equal or proportional to the mass over the area. Okay, but the other equation we said the area is equal to pi times 3m over 4 pi rho to the 2/3, and therefore the area is proportional to m to the 2/3. So we can basically put this into there to say that velocity squared is proportional to the mass over the mass to the 2/3. So v squared is proportional to the cube root of m. Okay, and if we know that, basically what this means is as you increase the mass, we also increase the terminal velocity. Okay, that is kind of the final thing there. And yeah, people at Cheese basically said things there. Okay, all right. I'll take a screenshot of that. So that would be my approach to that question. It's always easier the second time you do it. Okay, let's move on. Let's have a look at the next question. Okay. A student investigates how the terminal potential difference across the battery varies when more lamps are added in parallel. They notice the terminal PD decreases as more lamps are added, and they plot the graph. Okay, so that one there basically shows how as you have a bigger external, as you have a lower external resistance, we have a bigger current and therefore a smaller potential difference. Okay, so this is like having, rather than having a variable resistor to alter the external resistance, we're just doing it by adding more lamps. Okay, right, define EMF. Okay, so EMF, it's a definition that you just need to know. I would say for this, normally maybe a 1 mark answer, but I would say that this is going to be the work done per unit charge. So work done per unit charge of the power source or the source as energy transferred to the circuit. Okay, so the EMF is the energy transferred to the circuit. The potential difference is the energy transferred out of the circuit across a component. How does that compare to what they say in here? Work done per unit charge when other types of energy are transferred to electrical energy. That's not true, I don't think. There's no such thing as electrical energy. That's not a way that energy is stored, but we transfer by doing electrical work. So I'd say that that bit's incorrect, but the work done per unit charge when energy's charge of the source as energy is transferred to the circuit. Okay. There's also, yeah, there's basically lots of different ways that you can state that, so I think that's fine. Okay, determine the EMF of the battery and its internal resistance. Give your answers to 2 significant figures. So for this one, my approach would be to work this out. It's based on the practical that you should have carried out by now, where if we know that the EMF is equal to V plus IR, and we plot V on the y-axis, then we can say that that's equal to the EMF minus IR. And if we rearrange this into the format of minus RI plus E, if on the graph we plot V on the y-axis, we plot the current on the x-axis, then that means the gradient is equal to minus R, and the y-intercept is equal to the EMF. So the gradient is equal to minus the internal resistance, and the y-intercept is equal to the EMF. So we can do that fairly quickly by looking at the graph. I'm going to extend the line back, so again I think using a ruler and a pencil is definitely the best way of doing that. So I'm just going to take this line, I'm going to go back, and I reckon, is that right? Yeah, I reckon for this, I would say that the y-intercept C is about 9, well I don't know, this is the advantage, I just need to get a rubber. by the way, while I'm doing this, if you haven't already had a look at it, I am doing masterclasses this weekend for AQA, where I'll be going over some of the more tricky parts of the specification. Is it going to be 9 or is it going to be more like sort of 9.5? I reckon doing it for a second time. Oh, this is why I'm using a pencil. Otherwise I will be making mistakes. Because I guess there's a thickness of the line here. Yeah, so I reckon going back, looking at this in a bit more detail, I'm going to say that's about 8.9 volts. So reading off the y-intercept, the EMF is about 8.9 volts. The internal resistance, well, we need to work out the gradient. I'm going to do it from, let's say, this point over here. So you've got to draw the longest triangle possible. And I think it's really good to actually show that on your graph. Okay, so I've drawn a triangle. We can now look at the gradient. So the gradient is going to be equal to the change in y over the change in x. And that's going to be equal to 1.0 take away 8.9 divided by, in this case I've got 5.2 take away 0. So that's going to be about 7.9 divided by 5.2, which is minus 1.52. So I'm going to say R is going to be plus 1.5 ohms. So that'd be my approach to that. Yeah. If you just read 2 points and have 2 equations and 2 unknowns, will you get the mark? Hopefully not, because that's a bad way of doing things. Okay, you need to do this by using the gradient. That's why multiple data points were plotted, and therefore to get the mark for this, it's the gradient that you're looking at, and therefore I do feel that you need to show that you've calculated the gradient in order to find this value. Okay, is that the answer they've got? Yes. Okay, that's good. All matches up. That's nice. Right. Explain what happens to the terminal potential difference across the battery as more lamps are added in parallel. So basically, 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over Rn. So basically what we can say is the total resistance of the external circuit decreases as more lamps are added. And if you've got a lower overall resistance, this will then increase the current that could be drawn by the cell. And so with a greater current, the terminal PD decreases. If I was in the exam, I'd make my writing a little bit neater. Basically, because this is equal to the EMF minus IR, okay, and E is a fixed value and R is a fixed value, as you increase the value of I, we're multiplying the same resistance by a bigger value, and therefore we're going to have a bigger number taken off the EMF, and so as I goes up, those two things are constant, and that means the terminal PD goes down. Okay, Adam, it's basically, in the masterclass I will be doing a lot of the content. I'll have a few examples. If you are, I'd say that the masterclasses I'm doing, there's going to be a range of stuff there, from people who are kind of sort of like middling to also people who kind of need that support and reminder of all the things that they hopefully have done in school. But I will be doing things like Newton's third law, some potential divider things, and kind of really sort of how to push the top end. So I think it's worth going along to. The people who've been so far, there's been a whole range of people doing it, and many students are kind of aiming for an A star. So yeah, I think it's worth doing, and you can have it on in the background. Yeah. How to join the masterclass. Basically what you need to do is go to A-level physics online here. And basically, I can't point to it. Yeah, basically, if you go to alevelphysicsonline.com, when you go to the website, you can go to any page, or definitely the home page. And if you go to the home page at alevelphysicsonline.com, a little window will appear like this. Or it would do if it was the first time you went to that page. And basically on the front page it says book here, and then all you need to do is select the masterclass. So for example, book your class now for AQA physics. You go there, and then you just click if you want Saturday or Sunday, and if there's still spaces, then you just click on next, and then you can book your place. Okay, that's all there is to it really, pretty straightforward. Hopefully that's all working. Okay, yeah. Will there be a recording afterwards? Yes, there will be. I'll send out a recording of the masterclass afterwards. Okay, this question here, I think for me it just messed with my head. So, so this is a difficult question, and I don't think, as much as this says it's a predicted paper, I don't think that this question will come up again. I think that this one here is too difficult because we've got two different sources of EMF. So what I'm going to do is, rather than confuse myself, I'm just going to ignore it and move on. And I don't think that this part of the mark scheme is correct. I think that's incorrect, because what we have here, although if we ignored this part of the circuit and just thought, well, we've got a resistance and we've got a potential difference across this resistor, if you just had this 8.5 volts across a 2.9 ohm resistor, it would give you this value for I2, but then that negates the fact that we've got opposing it a different current going through that due to this 6 volt supply, which has an internal resistance of 3.5 ohms. And therefore, I don't think that's the right answer, but I haven't worked out what the right answer actually is yet. So I think there might be a mistake in the mark scheme. Yeah. Okay. Right. Somebody asking about the things. Yeah, the masterclass is on Teams, but you don't need to have Teams to log in. You can just join in the browser window. Teams works quite well because it just means that you can join. There's no video, there's no voice, and that means you're anonymous in the chat and everything. But you can still ask questions throughout. And Teams seems to work pretty well so far, but you don't need to have a Teams account. But yeah, basically you don't need a Teams account if you're going to go to this thing. Does the battery still provide a PD if it's charging? Yes, because initially it wouldn't. But then as you start to charge the battery up, it would then have its own potential difference, which is opposing the thing that's charging it. Yeah. Yeah. So I'm going to leave that question and maybe come back to it later or ignore it. I thought it was too difficult. Right. In the space below, sketch the third harmonic. So my approach to this is, first of all, use a pencil. And I'm going to choose something where I've got something which is a multiple of 3. So I'm going to go up to 12, and I'm going to put a bit here, and a bit here, and a bit here. So basically, this is my sketch diagram. Now, to show that we've got a fixed end, I think it's really important to show, and this is this is the way that we tend to do things to show something is fixed. I'm just going to put like a sort of hatched line on the other side. So this must be the end of where that string is. Now, if it's the third harmonic, and we've got fixed ends, we're going to have a node at each end, and we're going to have a node here and a node here. So I've just did some marks here to show that basically we get something like this. I'm going to turn the page around, and I'm going to do that, and that's basically my sketch. Okay, sometimes you can also show effectively the other way, so I'm just going to do this very lightly here. Okay, so it's easier when you have your hand on the inside of the curve, and therefore I've got that sketch. And I guess what I'd also do potentially is you can always put there's a node here, a node there, a node there, and a node there. Okay, so that would be my approach to that, which I guess is similar to how they did it over here. Calculate the frequency of this harmonic if the speed of the wave through the string is 300 meters per second. So for this, we need to look at the wavelength. Now, effectively, if we... Okay, we've got the length of the string. It says up here. That's going to zoom out a bit. So we know the length, and here, that length is equal to 1.5 wavelengths. Okay, because the wavelength is from a node to a node to another node, and therefore this is one wavelength. As we can see, the wave goes up, down, and back to the middle, so that's one wavelength. So this length is 1.5 lambda. So the wavelength is going to be equal to the length of the string divided by 1.5, which is 0.650 meters divided by 1.5, which is 0.4333 meters. And then the frequency, well, we can say that the wave speed is equal to f lambda, and so the frequency is just the wave speed divided by lambda, which in this case they gave it as 300, which doesn't seem the value I'd expect. I guess 300 is more like the speed of a sound wave in air. That seems like a different value to what I'd expect. I'd expect it maybe a bit slower than that for the speed of the wave in that string. And then we divide that by 0.4333, the number I've saved on my calculator. That's equal to 692.3. So I would say three significant figures, 693 hertz would be my answer. Right, for some reason, they've given it to two significant figures, but I'm not quite sure why. They've given the speed as 300, so that's three significant figures, because trailing zeros add to that. And then 650 is that's to three significant figures. So the final answer should be to three significant figures as well. Okay. So 692. My mistake. By the way, this is why it's quite good to be doing this with a live audience, because you see my silly mistakes. Yeah, so 692 would be the answer. And I'd expect an answer of three significant figures, because we've got three significant figures in the raw data. 650 is three significant figures because the zero adds to it. Otherwise, if you continue that logic, you say that 300 is only one significant figure, so I'd have to give my answer. If we said that 300 was one significant figure, then I'd have to give my answer as 700 hertz. Okay, and that can't be right. Okay, so if 300 was one significant figure, then we'd have to give our answer as one significant figure, which would be 700, which isn't correct. So that one there should be given to three significant figures. Explain how the strings of a guitar can give different fundamental frequencies despite having the same length and being made from the same material. Okay, so this one here I think links back to, and I think AQA tend to call them harmonics rather than fundamental frequencies. So I would say, looking at what the equations are, it says here that the fundamental, or the first harmonic, is equal to 1 over 2L root T over mu. So they have the same length, being made from the same material. I guess there are two things that we can do. In order to change the frequency, then what we can do, we can either change the tension, and you do that by using the bits, whatever they're called, on the end of a guitar. So you can change tension, or what we can do is, if they're made out of the same material, well, they might have, we can't really, the only thing I guess we can do is to change the mass. We can change the thickness, which will then change the mass per unit length. So you can change the tension or the thickness of the wire or the thickness of string, and they're the only two things that you can do if you've got a fixed length. So I would say here, the turning pegs, there you go, that's what they're called. So yeah, so I guess if you've, I think the question is maybe not so clear. If you've got the string, so basically each string will have a different thickness, which is why different strings of the same length have a different fundamental frequency. And the way we can adjust it is by adjusting the tension for the first harmonic. Okay. Yeah, that would be my approach. And also you'd write out a lovely kind of answer for that. Right, this one here, I had a look at it. I've not actually done it yet, but let's have a look. So the spongy part of human bones have a honeycomb-like structure. The structure provides strength, blah, blah, blah. We've got the compressive strength is 135 megapascals. A man of mass 85 kilograms jumps from a distance of 2.5 meters. We're going to assume that's a vertical distance. Determine the impact force if it takes 0.1 second to make a hard landing. So my approach to this is, first of all, is to write down that. Okay. Oh yeah, by the way, somebody said just in the chat here that the equation could only be used for the first. Yeah, so that last equation that I've got here, the equation about F equals 1 over 2L root T over mu, that can be applied to the first harmonic, because effectively 1 over 2L is related to the wavelength of that first harmonic. But you can basically use that equation where if you've got a different, because I think the velocity, okay, right, here's the thing, the velocity of that wave is equal to root T over mu, okay, and of course we know that the velocity is equal to F lambda, so the frequency is equal to the velocity divided by the wavelength. But this velocity here is equal to root T over mu. So the frequency is equal to 1 over the wavelength times root T over mu. Okay. Now it just happens to be that for the first harmonic, lambda is going to be equal to 2L. So the equation that says F is equal to 1 over 2L times T over mu, that's applicable to the first harmonic. But if you had the second harmonic, where the wavelength is equal to the length, then we could work out the frequency of that as 1 over L times T over mu. Okay? It just happens to be that AQA give you the equation in this format, Edexcel give the equation like this, and therefore that can be applied for all different harmonics. Okay. I will be saving the live, don't worry, this live stream will be saved and I'll be putting it up so you can just watch through and skip forward through any question that you might need. Are we only on question 5? Oh my gosh, there's like 28 pages at least and I'm only on question 30. I'm just going to have a quick sip of tea. By the way, how's everybody? Everybody doing all right? Hopefully you realise that in a week's time, paper 1 will be finished and you'll have done it. Okay, nice to have a mug with physics online on it. Okay, yeah. Right, what do you look out for in questions to know when to use that? Basically, anything to do with motion, that is a big bet. So, the distance is 2.5 meters, and we'll assume that's a vertical drop of 2.5 meters. It takes 0.1 seconds to make a hard landing. Okay, we'll maybe come back to that in a second. Do we know... Okay, so if they're jumping, their initial vertical velocity is going to be 0 meters per second. The acceleration is 9.81 meters per second squared. And then we can work out their final velocity. And then we can use that with Newton's second law that basically says the force is equal to the rate of change of momentum with respect to time, and that change in momentum is going to be equal to their mass times their final velocity minus their initial velocity over a certain change in time. Okay, so in order to work out this, we need to know how quickly they impact the ground. So basically, we've got a person, and there's two parts to the journey. The first part is as they're falling, and then the second part is once they've actually hit the ground and they're then decelerating. Okay, so for the first part, we need to work out how quickly they actually hit the ground. So we've got SUA. We can say then that V squared is equal to U squared plus 2AS. So V is going to be the square root of 2 times 9.81 times 2.5. So V is 2 times 9.81 times 2.5 square rooted is 7.003, all that. So that's a lovely number. Okay, now in terms of the force, that force is going to be equal to their mass, which is 85. And this 85 kilogram person, their final velocity is 0, but their initial velocity as they hit the ground is 7 meters per second. So their change in velocity is going to be equal in size to basically minus 7.004 meters per second. And that happens over 0.1 seconds, which is 5953. So to two significant figures, that's going to be 5.95, so that's going to be 6.0 times 10 to the 3 newtons. Okay, so I'm going to give this as 6,000, but to show it's to two significant figures, because we've got two significant figures in the question, I'm going to write it in standard form to show that. Okay. Okay. How do you get the predicted paper? Yeah, this one is on the PMT website. It's not predicted, it's just some good practice questions that you can work through, which is what I'm doing now. So I don't think this question will come up necessarily, but this type of question can always be asked in an exam. Did I switch U and V? Yeah, so basically this V here, for the first part of the journey, is now going to be U for the second part of the journey. Okay, but we just want to look at the size of the force, not the direction, and therefore that's why it becomes, because effectively as they're decelerating, their initial velocity was 7 meters per second, and their final velocity as they stop on the ground is going to be 0. So now that V is now the U in this second part of the thing. So this thing here is related to this second part of that motion. Okay. Okay, so this is the force that's acting on that person as they change their momentum from moving to stopped. By modelling the femur as a cylinder with a cross-sectional area of 65 millimeters, so always draw a diagram. That seems to me quite a small number, because if the area is 66 millimeters, so 65, that's like saying that your femur is 8 millimeters in diameter, or about 10 millimeters. So basically, yeah, so this is basically modelling the femur, which I guess is one of the largest bones in the body, as something that's got a cross-sectional area a bit like this pen. Okay, but you may assume that the braking stress and ultimate compressive stress are the same. Well, basically stress, we can actually work that out in this example up here. The stress is going to be equal to the force divided by the area, which is this number here, and I'm going to use my calculated value, 5953, divided by this area here, which is 65 times 10 to the minus 4. The reason is that a millimetre is equal, 10 to the minus 6, isn't it? Okay, so a millimetre is a metre times 10 to the minus 3. So a millimetre squared is going to be the same as 10 to the minus 3 squared, which is 10 to the minus 6. So that should be a 6 down here. So we've got 5953 divided by 65 times 10 to the minus 6 gives me an answer of stress is equal to 91 megapascals. Okay. Yeah. And yes, for the people asking, I'll keep the recording up so you can look at it over the next couple of days. Provided, of course, you will come along to my masterclasses I'm running this weekend. And that allows me to kind of keep making more videos like this. Right, so 91 megapascals is the actual stress. And then we need to compare this 91 to the stress given to us at the start of the question, which was 135. And we can say that the stress of landing is going to be smaller than the ultimate compressive strength. So what we've got to do is actually, maybe put these numbers down so we can say that 91 is smaller than 135, and therefore the femur won't break. However, thinking about the dimensions, this is more like the kind of width that you'd have on a bird's leg than maybe a human. Okay, so that would be my approach. Now, the next one, 3 marks long. How are we doing for the questions? By the way, I don't know how long this live stream is now. Yeah, right. When are the next masterclasses for paper 2 and paper 3? I haven't got the dates in yet, but I will be doing masterclasses. I've done some recently for paper 1, so hopefully the people who've done those have enjoyed them. I did a free one on electricity. I did a lovely one, hopefully lovely, but I did one all about refraction the other night. I've done them for AQA, EdXL and OCR for paper 1. I've got some more this weekend. And also I will be doing some paper 2 and possibly paper 3 masterclasses. If people want me to do them, I'll put them on and hopefully somebody will turn up. Yeah. Right, the next question then, even though the femur won't break, well actually that told you the answer to the last question actually. There's still a risk of fracture to the smaller bones such as the tibia and fibula as well as the spine. They say that by bending the knees their impact force will be significantly reduced and therefore that it should be safe to jump from a height of 2.5 metres. Explain whether John is correct. So the force is going to be equal to the change in momentum over a change in time, and that means that the force times a change in time is going to be equal to a change in momentum. Now the thing is, if you're jumping from that height of 2.5 meters, you will always have to change the momentum by the same amount because you're always going to be impacting the ground at that same initial velocity of 7 meters per second. But if you were to increase the collision time by bending your knees, for the same change in momentum, we then have a much smaller force applied. So they say that the impact force will be significantly reduced. So that means John is correct that the force will reduce as knees bend and collision time increases. Okay, so that's true. However, and that therefore it should be safe to jump from a height of 2.5 meters. They are not necessarily correct because if you've ever jumped from that height, it is quite difficult. Speaking as a former paratrooper who did lots of jumping from things, including jumping from heights as you do lots of the training, I would say, however, jumping from 2.5 meters is still not safe. And if it is safe, you need to make sure you're wearing combat boots, 2-footed landing, and then you roll out of it, speaking as a para-trained former soldier. Okay, right. Of course, you can also then add some things to say the fact that there might be some compression of the spine, which I guess it's talking there. You might still break some of the smaller bones, especially if you're a bit weak. So, the next question has a load of stuff. The first bit is like a real question. You can ignore it. It's just context that you can ignore. The second bit, we've got the weight of the car resting on 4 springs. We've got a mass here. We've got Harry sitting on top of the car. Quite a boy-centric paper. This one we had John last time. Now we've got Harry. We've got the car oscillates up and down, completing one oscillation in 1.12 seconds. So that's our time period. This picture, yeah. I mean, it shows a car. I wouldn't say, though, maybe a car from the 1890s. Right, determine the spring constant for the combined four-spring system. So this is just a GCSE question, isn't it? We've basically got, or maybe a little bit more than that. We're going to be using the equation that says the time period is equal to 2 pi root m over k. Okay, so if the car's oscillating up and down at its maybe natural frequency, we can work out the time period. If we know the mass, we can then work out the combined spring constant for those four things. So we can say that t squared is equal to 4 pi squared m over k, and therefore k is just going to be 4 pi squared m over t squared. That'd be my approach, which is equal to 4 times pi squared times 1200 divided by 1.12 squared. So I've got 37766. So I would give this as three significant figures. So 3.78 times 10 to the 4 newtons per metre. There we go, bang on, same answer as they've got over here. The reason being that we're going to assume that if they've given it like this, that's four significant figures with the trailing zeros, that's three significant figures. So if I can give this to three significant figures as well. Okay, what do people say in the chat? 1 mark. Yeah, I think that would probably be 2 marks in a real exam, but you know, it's just an indication of the type of question. The fact there's 4 springs just gives us the combined spring constant of 4 springs in parallel. That's all it is. So basically, this is just the spring constant for our 4 springs, all of them in parallel with each other. Okay. 4 times 10 to the 4 would be incorrect because that's only one significant figure. So therefore, I think the answer has to be 3.78. Okay. Why did I square the time? Yeah, so basically, because we've got the time period equal to 2 pi root m over k, what I've done is I square this, I square that, I square that, and I square all of this to get m over k here, to then make k the thing that we're then rearranging to. So that's why I squared everything to give t squared is 4 pi squared m over k to work out what k is as I rearranged it. Okay. Right. State the conditions necessary for the car to be moving with simple harmonic motion. Basically, we need to say that, and it's basically based on this equation here. Basically, what we need to say is that the acceleration is proportional to the negative value of its displacement. And I guess it's that displacement from its equilibrium position. Normally, this would be a 1 mark question at the start, which would then give people a clue that we need to use a simple harmonic equation to actually work out the spring constant. So normally that would be question 1 and that would be question 2. While they sat on the roof, his weight of 835 newtons was supported by each of the 4 wheels equally. Calculate the initial amplitude, and assuming it oscillates with SHM, which it is, because I guess we have to assume it's SHM, otherwise we couldn't have done question 1. Determine the maximum acceleration of the car as it oscillates. So, right, the initial amplitude is what we're trying to find, so A is what we need. And I guess, trying to think about this, I'm just working out how I do this. In order to work out, calculate the initial amplitude of oscillation, and then work out the maximum acceleration. So A max, the acceleration max, is going to be equal to A omega squared, or omega squared A. We know omega squared because we know that the time period is equal to 1.12, so we can use that to work out omega, and therefore we just need to work out A. So I'd say that because we know the force is equal to kx, and we've worked out k, we can work out this x, which is going to be x max, and therefore the force applied is going to be equal to the spring constant times the amplitude of motion, because when they get off, that's then going to cause it to go up. So the amplitude is equal to the force divided by the spring constant. The force that they provide down is 835, and we're going to divide that by 37766, the spring constant in newtons per metre. Okay, so the amplitude is going to be 835 divided by this. Is that right? Yeah. So the amplitude is going to be 0.0221 metres, and therefore 2 pi over t squared times 0.0221. Am I doing this right so far? I think I am. We don't use the car's weight because what we're assuming is that, oh no, actually, is that right? To the equilibrium position of that oscillating system, but then Harry provides an additional force on it that makes it go down a bit, and then as the car oscillates, it's going to be oscillating through the equilibrium position, which is caused by the weight of the car. So we only need to consider the weight of Harry, which is causing that car to oscillate. Okay? Yeah. So we're going to multiply that. So we've got 2 times pi divided by 1.12. I'm going to square that. And this gives me A max equal to 0.696. So I would say then that's equal, yeah, to 0.696 meters per second squared. So how's that compare to this? Yeah, for some reason they rounded it to 2 significant figures, but it should be to 3 significant figures, because that's the raw data that we have in the question. That's 3 significant figures, and on the first page they gave the mass and the time to 3 significant figures as well, so that should be to 3 significant figures. Okay, the displacement comes from the displacement A is equal, so the amplitude is going to be the maximum displacement. So if we imagine we've got a spring, okay, so basically there's a spring on that car, and when Harry's on it, he's basically compressed it by a certain distance x, which is going to be effectively the extension or the compression of that spring. So basically this is the car spring in its equilibrium position. Harry gets on it and it goes down by a certain amount, and the amount it goes down is going to be equal to the amplitude of the oscillations, because when they get off, the car then goes up and down several times. Okay, and therefore this amplitude that I worked out here is equal to the maximum displacement, and we can work that out just using this equation here that says the force is equal to the spring constant times the extension. Okay, so that's how I worked out the amplitude, and then you just multiply the amplitude by omega squared to find A max. Hopefully that's all right. Yeah, and so basically the car's weight has just compressed that spring to its equilibrium position about which it oscillates, and it's the additional weight of Harry that causes it to oscillate like this. Okay, so this question here, if you get an explanation question, then I think it's really important that you can still draw in a diagram. Okay, and if you draw in a diagram like this that shows something resonating, where you maybe have the amplitude of the maximum oscillation as we have the frequency of the driver, then basically this is the kind of thing that you need to think about. And if you've got something where the natural frequency is equal to the driving frequency, we're going to get maximum energy going into the system, and we get resonance. So it says here, and this question is very much like a question about a boat. I think it was an OCR question, I think it was, where there was a boat that was going over waves, and they were like trying to work out, is it better to go with the waves or against it? Okay, so let's have a think. So the time between the collisions, so imagine there's Harry, the distance he travels is 10.5 meters at a velocity of 9.4 meters per second. So that's meters per second, okay. So the time is going, well, if speed is distance, I always have to write it, speed is equal to distance over time. So time is going to be equal to the displacement divided by the velocity. So that's 10.5 over 9.4, which is 1.12. So that means the time between the bumps is equal to the time period of the system. Okay, now an assumption here would be that before we knew the natural frequency of that object when there was only the car that was oscillating. Now what's happened is that Harry's got into the car, so the mass of the system would go up, so actually the natural frequency would be different to how it was before. So basically we can say that the time period between the bumps is similar. I'm going to write that again. Okay, so basically the time between the car hitting the bumps is similar, but not necessarily the same as the natural time period of an oscillating car. So it would start to resonate. And basically what that means is, rather than just the suspension absorbing that bump, as you go over more bumps, the amplitude of the oscillations gets bigger and bigger and bigger until it's kind of controllable. Okay, right, so what are people saying? JJFO4 says the mass was to two significant figures. So I think in the previous part, the mass has been quoted in this. So the mass has been quoted to 4 significant figures. So that is equal to 4 significant figures. If it was to 2 significant figures, it would have to be given as 1.2 times 10 to the 3 kilograms. And then that would be the mass to 2 significant figures. So yeah, so 4 significant figures is the raw data, which is why it gave the answer to at least 3 significant figures in that final part. Okay, it was my approach. So yeah, for this one over here, we've basically got a nice scenario where we can actually calculate what the driving frequency is from this, and we can relate that to being similar to the natural frequency, and therefore we're going to have a region maybe somewhere up here where we've got large oscillations as that car starts to resonate. Okay, that'd be my approach. Okay, right. Cool. Yeah. Basically, the thing is with A-level physics is it's a bit of like A-level maths and A-level physics are very different. And I did a video a few years ago with Tom Rock's maths, so we did some questions together. Now, a lot of the time in A-level maths, they'll give an answer of like a third as 1/3. and that's seen as like the right answer. In physics, we'd have to give it as maybe 0.33, and we'd write it as a decimal because the number of decimal places is related to the number of significant figures, which I guess is based on the raw data that you're using for that. So a lot of the time in A-level maths, for people doing these papers, often people write 3 significant figures. With A-level physics, it's a bit more artificial, and it's very much an artificial way of actually the way the numbers are presented. However, it's nothing to worry about. If you mess up significant figures, it's going to maybe drop you 1 mark on the whole paper. So yeah, it's nothing to worry about too much. Right. Multiple choice. Thankfully, we're near the end. Right, so this first one, the approximate order of magnitude of the length of a person's forearm. So I guess this bit here on me. So if I look at my forearm, it's going to be about, what's that, maybe, is that my forearm? Maybe 30 centimetres. So this is just like 30 centimetres, which I think, looking at this, I would say 30 centimetres is, well, effectively that's 1 metre, that's 0.1 metres, that's 0.01, and that's 10 metres. I would say it's going to be in the order of 10 to the minus 1 would be my thought for that. So what do people put in the chat? For the number 7, if you could put 7 and then the letter that you guess, I would say that my arm is closer to 10 centimetres than a metre. And so I'd probably give the answer as B. So that would be my approach to this. In the chat, let me know what your answers are. So we've got Potato Monk says C. Other people I'm sure are going to start putting their answers in quite soon. So if you put a number in front of the letter, I know exactly which question you're talking about. So we've got Salvi Myers says 7B. 7B says R7T. D, somebody's got a long forearm. There's some elephants in the chat. Okay. 7B says coding with Ronak. 7B says cosmic. Yeah, I would say 7B, but of course this is just an estimate. Okay, and I suspect a lot of people here, because this is basically midway between the two. So it's 30 centimetres closer to like 10 centimetres or a metre. I'd say probably B. But I would say that actually everybody in the chat's got different answers. So if you put 7B or 7C, I'm sure you'd get the mark. Okay, what are the correct base units for power? So this is a nice one. All of you need to know base units. So base units for power. So power is equal to the rate of energy transfer. And therefore we need to think about what we might measure energy. And so I'm going to just think about kinetic energy being equal to a half mv squared. So the base units for energy are going to be the same as whatever we measure mass in. So that's a kilogram. And then we've got meters per second squared. So that's going to be meters squared second to the minus 2. And we're going to divide that by time. So we'd be doing all of this divided by seconds. So it'd be kilogram meters squared second to the minus 3. So the answer for this is A. Okay, so that would be my answer for that. Okay, yeah, don't worry about the mark scheme. I think it just says C, but, you know, don't forget that this is just maybe a starting point. And obviously the more people do questions, you kind of realise that actually things can be adjusted, or there might be multiple answers, especially as this is only a practice paper. Okay, right. Right. The next question, number 9. What is the correct order for the strongest to weakest of the 4 fundamental forces? I think for this one, this is something that AQA don't actually assess. I believe that AQA only ask you to be able to recall what the 4 fundamental interactions are. And they often call them interactions rather than forces. So you've got the strong interaction, so the strong nuclear interaction, the weak nuclear interaction, the gravitational interaction, and the electromagnetic interaction. But which of these is the weakest? The weakest has to be gravitational, which is like several orders of magnitude weaker than the others. So strongest to weakest, this one here must be the correct, because the weak isn't the weakest of the forces, and therefore the answer for 9 I think would be D. Is that what this says? Yeah, that's what it says as well. Okay, a particle has a quark composition of down, anti-up. So if it's made out of a combination of a down and an up quark, then it must be some kind of pion. Okay. Now if we look at what the charges are, a down quark has got a charge of minus a third, and an anti-down has got a charge of minus 2/3. So that's just the charges on the two quarks, and therefore the overall charge is going to be negative, and it's going to be therefore a negative pion. So it's got a charge of 0, that's not correct. It's a baryon, no, because it's made out of two quarks. It's not a lepton because it's made out of quarks, and therefore it is a pion. So the answer for 10 is A. 10A, as people says. Potato Monk. Saxion. I can't say some of these names. Dear 10A. Yeah, good. Somebody says it can't be a pion. Cosmic. Why is it not a pion? If you look at what you have to remember, you need to know about the quarks and mesons, and a down, anti-down. So your down, anti-up is a pion. That's just one of the bits of facts you just have to remember. Okay, the following decay is not possible. Why is that? So for this, if there's anything that you're maybe not sure about, I'd just start by looking at things like charge, baryon number and lepton number and write it underneath. So we've got a charge, I think this is the thing that they had at the beginning of the paper as well. If you've got an up and a down and a strange, that quark combination would have a charge equal to 0. Is that right? Because you'd have 2/3 minus a third minus a third, so that's 0. That's got a charge, if it's an up, down, down, that's going to be 0. That's going to be -1, and that's going to be 0. So charge is not conserved actually is the right answer. Okay, baryon number 1, 1, 0, 0, lepton number 0, 0, 1, -1. So lepton numbers conserved, baryon numbers conserved. So that basically that's an incorrect statement. That's an incorrect statement. Strangeness is not conserved is true, but that doesn't mean it can't happen, so therefore charge is not conserved. So my answer for 11 is C. Okay, right. All good so far? Should we do a few more? Oh, here we go. K plus meson decays into a pion plus and a pion naught. Which of the following statements is correct? Now, the first one you don't know because you don't need to know the strangeness of a kaon. Okay, I don't think, or do you have to know the strangeness of a kaon? Okay, a kaon. Actually, no, you do. You need to know that a kaon, the quark structure, is up anti-strange. This one here is going to be up anti-down, and this one is going to be down, either down anti-down or up anti-up. So, yeah, 12. Is it A, B, C or D? Let's see what people think. A lot of people are saying B. So, this is it a strong interaction? And therefore strangeness should be conserved, but it's not. Okay, so I would say here the answer for this is B. Okay, strangeness is not conserved is because that's got a strangeness of +1 because it's an anti-strange quark, so it will have a strangeness of +1, but that's not conserved, and therefore that one there, 12B, is the right answer. Okay, nice question. Do you need to... I don't think you have to know how kaons decay, but you might be given kaons as part of like a decay reaction or interaction, and therefore you need to know that they will decay to other things, but you don't have to remember exactly what they're going to decay to. Right, monochromatic light on a metal surface, no electrons emitted from the surface. If you increase the intensity of the light, that just means, so imagine at the moment we've got basically like a low energy photon. So a low energy photon hits the surface of a metal and no electrons come out. If you shine more of these low energy photons at that surface, none of these photons have enough energy to liberate an electron, and of course it's going to be one photon interacting with one electron, and therefore if you increase the intensity it will have no effect. The work function stays the same, no photoelectrons emitted, so here the answer for 13 is C. Great stuff, great stuff. Coding, Salvi, is that Dia? Yeah, the styrofoam, 13C, great answers, right. This one here, I would say what you need to do is, if it's a numerical thing, don't look at the answers. Treat it like a normal question, and that means you just need to work out the actual thing. So we've got energy of photons, so we know that E is equal to HF, or the energy is equal to HC over lambda. And I would say then that it says the phosphor, basically we have a photon that comes in, so basically, yeah, a photon comes in, an electron goes up an energy level, and then it drops back down. But because the electron is absorbing an ultraviolet photon and emitting a visible photon, we need to look at the energy lost to heat. So we're basically looking at this amount of energy. So we can do that by looking at this energy and take away that energy. And that change in energy is going to be equal to HC times 1 over lambda, take away 1 over lambda of the two different photons of these different wavelengths. So my approach would be just to do 1 divided by 254 times 10 to the minus 9, take away 1 divided by 450 times 10 to the minus 9, times 6.63 times 10 to the minus 34 Planck's constant times 3 times 10 to the 8 is 3.41 times 10 to the minus 19 joules. Okay, so still, even though it's multiple choice, you can still write down the equations. We know that from the data sheet. You know that's 6.63 times 10 to the minus 34. You know the speed of light is 3.00 times 10 to the 8. And therefore, without looking at the numbers, do the calculation and then look at the numbers so you don't get distracted. Okay, right. Does physics get way harder in year 13? No, it's all fine. It's all fine. Okay. Is it Divya? Divya. Okay, right. Sorry if I'm saying your names completely wrong. Divya. Okay, cool. Right. Right. This next question. The following diagrams show some of the energy levels for hydrogen. Which of the transitions shown to result in the greatest possible wavelength emitted? We already did this last time. We know that the energy is equal to hc over lambda, and therefore lambda is equal to hc over E. So basically we're going to get the biggest wavelength when we have the smallest energy transfer. And the smallest energy transfer is this one here, from 3 down to 2. So we're going to have the lowest frequency, longest wavelength, and therefore here the answer for 15 is A. Great stuff. Right. Okay, right. What is the correct expression for the de Broglie wavelength of an electron in terms of its kinetic energy? So its kinetic energy, Ek, is going to be equal to a half mv squared, and the de Broglie wavelength, lambda, is going to be equal to Planck's constant over its momentum. Okay, so that would be my starting thing. And then, of course, I guess you need to relate the momentum to the kinetic energy, which isn't actually an easy thing to do, is it? Okay, let's have a look at this. Right, so there is an equation that says basically the kinetic energy of something is equal to p squared over 2m. Okay, so this is something that might come up with Edexcel, and basically we can say that from this thing here, I was going to do it in here, the momentum is equal to h over lambda. Okay, so okay, I see. So basically, the momentum p is going to be equal to 2 times the mass times the kinetic energy, square rooted, and we basically put this into that to say that the wavelength is equal to Planck's constant divided by the square root of 2m ek, or e as they put up here. So I think they've got the answer as D. Is that right? Yeah, so I would say at the moment, yeah, so basically that's the link between kinetic energy and momentum. And you can get to that, basically I'll just do it up here, so it's on a different bit of the page. If you know that the kinetic energy is equal to a half mv squared, and you know that momentum is equal to mv, then you can say that the velocity is equal to the mass divided by the momentum. So v squared is equal to m squared over p squared. And if you put that in up here, that means the kinetic energy is equal to a half times the mass times, is that right? Oh, so v is equal to p over m. So v squared is equal to the momentum squared over m squared. So that's equal to the momentum squared divided by m squared. So the kinetic energy is equal to, that's going to cancel, p squared over 2m, which is what we have over here. Does that make sense? Yeah, right. Okay, how are we doing? 17. What is the maximum order observed on the screen when this light is shone through a diffraction grating with 300 lines per millimetre? So for this question, let's have a look. What do you reckon people think? Is it A, B, C or D? Now my approach would be to say that d sine theta is equal to n lambda, and we want to know the maximum value of n when effectively sine theta is sine of 90 degrees. And basically if theta was equal to 90 degrees, then sine theta would be equal to 1, and therefore n is going to be equal to lambda over d. Okay, so basically if d times 1 is n lambda, then n is equal to lambda over d if we've got theta equal to 90 degrees. Okay, so what this then means is that we've got the wavelength, which is 430 times 10 to the minus 9, but we've now got 300 lines per millimetre, so d is going to be equal to 1 over 300 times 10 to the 3. So that's the same as this times 300 times 10 to the 3. So that would be 430 times 10 to the minus 9 by 300 times 10 to the 3. Is that right? Have I made a mistake? I'm getting an answer here. Oh yeah, it's d over lambda, isn't it? As everybody's saying. Yeah, sorry, d over lambda. Thank you to everybody who's telling me that. So d and other people. So that's going to be equal to 1 over all of this. I'm going to write it again. That's equal then to 300. Basically, when you do the maths, it's not that, it's going to be 1 divided by that, which is n is equal to 7.75. Now, of course, n has to be an integer, and it can't be above 7. So even though this is closer to 8, we have to go to the integer, which is at the bottom end. And so there would be 7 orders seen on each side of that central maxima. So you'd have 7, one in the middle, then another 7. And so the maximum order observed on the screen is going to be C. Does that make sense? Okay. Okay, right. How do I know sine is 90 degrees? Yeah, so basically for this example, I'm running out of bits of paper. For this example, imagine you've got a screen over here. You've got your laser that's shining through a diffraction grating. You're going to have your first central maxima here. You're going to have another one that goes here. So this is basically n equals 1. And then you'd kind of go out to like n equals 2 and so on. Okay. Now really, I guess there'd also be ones coming out here and here and here. And effectively, if you had an infinitely long screen, then maybe n equals 3, n equals 4, n equals 5 would eventually end on the screen. So this angle here is theta. Now the maximum that you could get to would be where theta is equal to 90 degrees. And basically you've got to have something where theta is smaller than that. So the maximum one would be where theta is equal to 90 degrees, which in this case, theoretically, n would be equal to 7.75. But of course, that means we never get to n equals 8, and therefore the one before that, where there's still an angle smaller than 90 degrees, would be where n is equal to 7. Okay, does that make sense? Right. The phase difference between adjacent antinodes on a stationary wave is, well, let's do a stationary wave. So here's a wave, and here we're going to have something like that. Okay, now if you've got a stationary wave, there's also going to be a point, maybe a small amount of time later, where it's in the other position, here, like that. Okay, now let's look at, we've got nodes here, here, and here. And here we've got an antinode, and here we've got an antinode. Now, these two antinodes are going to be adjacent to one another. But if we think about it, this is one full wavelength. And so the phase difference between these two things is going to be equal to, they're basically going to be out of phase or in anti-phase with one another. So when one is up, this one is down. If we think about this point and this point. So the phase difference is equal to half a cycle, because the two things are in antiphase, and therefore that's equal to pi radians. Okay, so the phase difference here is equal to pi radians, because when this one is up, this one is down. So my answer for 18 would be B. Does that make sense? Looking at this, that's not correct, because those two things, they're not adjacent antinodes. That's an antinode. The adjacent antinode would be here, and then there's another one here. So basically that's incorrect, that thing, I think, because from there to there would be equal to 2 pi radians. So that's not correct. So the mark, that thing there is not right, I'm afraid. So here, that's what we have. You've got an antinode. The adjacent antinode would be in antiphase with it, because when that one's up, that one's down, and vice versa. Why is it not pi over 2? Because in one wave cycle, you'd have basically 2 pi radians is equal to one complete wave. And effectively, here we've got half that cycle, so it's going to be pi radians. Okay, 2 points on a microwave with a frequency of 2.45 gigahertz are 0.15 meter apart. Determine the phase difference between the two things. So here is my microwave. Okay, now we know that the wavelength is going to be equal to the wave speed divided by the frequency. So that's 3.00 times 10 to the 8 divided by the frequency, which is 2.45 times 10 to the 9. So that's equal to 0.122 meters. Okay, so basically imagine this is a wave. If you've got a point here, there's going to be another point over here, which is the wavelength equal to 0.122 of a meter. But now we're looking at this point and this point over here. So we're not just looking at one distance here, we're going to be looking at this and a bit more. So effectively, we've got something which is 0.15 over 0.122, which is equal to 1.225 waves. And then if we multiply that by 2, okay, that doesn't seem to give, the phase difference is, okay, so that's the wavelength. The 2 points are 1.5 meters apart. So I guess if we know the path difference between these two things, we can look at the phase difference. What have they put in the mark scheme? So they've got 3 over 2.445. Okay, so if we multiply that by 2 pi, that's the same as 2.45 pi, and I guess we then go to what's that? 49 over 20. Okay, so 49 over 20 is a fraction of pi, so I guess the answer here is B. Okay, that's a bit awkward. Yeah, does that make sense? Yeah, so basically I went from this, I multiplied this path difference by 2 pi to get it in terms of a phase difference. So the phase difference would be 2.45 pi, but they've given it as a fraction of 49 over 20. Okay, right. Okay, 3 forces of these magnitudes are respectively acting on an object, which is not possible. Basically, if you add the 6 to the 8 to the 10, so you've got 6, 8 and 10, the longest possible biggest force that you could apply would be 14, 10, 24 newtons, and therefore you can't get to 26 newtons because it's too big. Something like this, you know it can't be the middle one, so it'd have to be the smallest or the largest. And of course you could have something where you had a 10 newton force, you had a 8 newton and a 6 newton, and you'd still get back to 0 if they're as a triangle. Okay, and this paper is easier than the past papers, yeah, definitely. A boy of mass 50 kilograms wants to cross a ditch by walking along a 20 kilogram uniform plank. So if that's 4 meters, at a distance of 2 meters, there's going to be 20 kilograms, so 20 G acting at 2 meters. There's going to be the plank rests on the bank at one end and on the rock in the ditch 3 meters. Determine whether the plank will tip before he reaches the end and how fast. So there's going to be a distance. So I guess if that's 2 meters from that end, that's also going to be 1 meter from here. And the boy of mass 50 kilograms. So I'm going to do a longer arrow, and that's going to be 50 G. That's at a certain distance D from this end. So when will they cause it to tip? So basically let's look at the limiting case. So I would say that if we think about the moments, when the anti-clockwise moments are equal to the clockwise moments, that's the kind of sort of the limiting factor. So the anti-clockwise moments are going to be the force times distance. So that would be 20 G times 1. And when we equate that to 50 G times D, D would be equal to 20 over 50, which equals 0.40 of a meter. So when the person's at 0.4, will it tip before he reaches the end at 0.4 meters beyond the rock? No, that's not true. Yes, the plank will tip before he reaches the end at point. That's true. That's true as well. What answer have they put here? Okay, that's my answer. Okay, sorry. You can't predict topics. The whole point is you cannot predict topics. These are just practice questions, similar in style to what could come up, but I don't think this question is going to come up. So, yes, the plank will tip before he reaches the end at 0.4 from the rock. I don't think that's true, so it's not this, because when the buoy reaches 0.4, they will still be in equilibrium. So even at 0.4 meters, the buoy, yeah. So that one there is a true statement. So the plank will tip before he reaches the end at 0.4 beyond the rock. Okay. So I don't think that's great grammar, so I think, yeah. Right. What do people reckon in the chat over here? So I would say the plank, yeah, it says, determine whether the plank will tip before he reaches the end. Yes, it will. And how far beyond the rock can he go before it tips? It says the plank will tip before he reaches the end. I guess that one's going to be the closest, but I don't think it's. I don't think that's not the right answer, because basically when they get to 0.4, it hasn't tipped, and that's like the equilibrium position. When they go beyond 0.4, that's when it tips. So I think this basically after 0.4 meters from the rock, it will tip. So I don't think that's the best way of phrasing it, but I think that's the one they want you to get. Okay, right, should we do another question? We've only got, what, 10 more to go? And of course, if you're watching this, I hope all of your exams go really well. I do have masterclasses I'm doing this weekend, Saturday and Sunday morning. Make sure you book now before they all go. Also, I think that if you haven't already done so, I do have a premium plan. You can buy a 6-week premium plan for A-level physics online. It's only £30, and this gives you access to all of my work solutions for paper 2, for paper 3A, and also the astro, medical, turning points and engineering options. So I've got videos where I go through the 2022 and 23 papers, all that good stuff. But by a premium plan, you've got access to hundreds more videos to help you in any area that you're not so confident about, and all the other bits and pieces on my website. So yeah, go and buy access to my website, buy access to a masterclass, and have a look at my shop if you want to find my practice papers for paper 3A. Okay, right, so yeah, go and buy some stuff. Right, let's go back to the question. A uniform 2-meter long wooden plank. Right, so let's draw this. So we've got a 2-meter long plank. So that means in the centre, it's got a mass of 6 kilograms. So I'm going to put that 6g at 1 metre. It's got a 4 kilogram mass attached to the left end. So that's 4g down here. And a 2 kilogram mass attached to the right end. So that's 2g. At what point from the left end should the plank be supported for it to balance? So we're just saying there's one force here, F. Okay. So let's say that this force is a distance d from this end. Okay, does that make sense? So I would say then that you could do this. We know that the force has to be equal to this downwards weight and that weight and that weight. So the force is going to be equal to 4 plus 6 plus 2. So the force upwards is going to be equal to 12g. And then the next thing I'm going to do is take moments about, I'm going to call that L, because that's going to be the left end. So I'm going to take the moments about L. So basically that's equal, so basically when there's 0 moments it's being supported. So we can say that the force here upwards, so basically we can say that 12g times d, so that's going to be my anti-clockwise moment, is equal to 1 times 6g plus 2 times 2g. And obviously the g's are going to all cancel. So we can say that 12d is equal to 6 plus 4, so that's equal to 10, and therefore d is equal to 10 over 12. Is that right? Which is 0.833. Okay, so D up here is A. So that would be my approach to that moment's question. Okay. Somebody says, are there any other good websites with good questions? Yes. Go to alevelphysicsonline.com and then you'll find a link to my shop where you can find practice papers. And I've got lots of questions which are really well written. There's been a whole team of us putting this together. I've paid other teachers to check it and I've paid other people to check it and stuff like that. So I've got lots of questions with mark schemes and model solutions. You can buy these. These are ones for paper 3A, but you can find those. Yeah. Right. And also, we've got another celebrity in the house. If anybody here is doing A-level biology, we've got Miss Estrick here in the chat. Hello, hope you're doing well. We did some videos together last week, so I put out one about flashcards the other day. So, yeah, basically, if you want to say hello to a biology celebrity, and if you've got biology exams coming soon, do say hello to Miss Estrick in the chat. Hello. Right. Okay, so we've got this. Also, that's actually a bit different. The way that real exam papers tend to give answers is that they tend to give them in ascending order. So it would actually give them in numerical value. So it wouldn't just start with 0.83, then 0.75. A real paper would have 0.75, 0.83, 1, 1.2. Okay, right. No way. We've got a load of people doing biology and physics. Awesome stuff. Okay, a rugby player kicks a ball at an angle of 40 degrees above the horizontal with an initial velocity of 15 metres per second. If the height of the goal post is 3 metres and the distance from the post is 20 metres, will the ball clear the posts? Now that is a lot of information, so what I'm going to do is just start with a diagram. So basically this is what happens, I think. Okay, so basically we've got this kind of scenario where that height is going to be 3 metres, that distance is 20 metres, and we know that the initial velocity is 15 metres per second at an angle of 40 degrees. Okay, the question is, will it clear the post? Will it hit the crossbar? So basically, if this is where the crossbar is, will the ball maybe go up and come down? Will it kind of just be going up? I think that's actually a lot of work for... I think that's a lot of work for 1 mark. So if I saw this in a multiple choice paper, what I'd be doing is basically ignoring this and coming back to it at the end of the paper, because I think there's a lot of work there to do, especially as you have a projectile motion question with Suvat equations in both horizontal and vertical distances. Okay, how did they approach it? So they've got horizontally, we've got a time of flight, and then I guess we can use that in the vertical direction. Yeah, so okay, so let's think about this. If we go horizontally, we know that the speed it travels at is equal to s over t. Okay, so the time is going to be equal to the horizontal displacement divided by the horizontal velocity. Okay, yeah, so what are people saying in the chat, by the way? Oh yeah, somebody's saying for biology, can you get all of the meiosis stuff banned from the spec? Do you know what? I'm a grown-up. I run my own business. I used to be a teacher, and I still don't know the difference between meiosis, mitosis. I have no idea what they mean, but it hasn't affected me in my everyday life. Okay, right, so the time then it takes is equal to the distance of 20 meters divided by the horizontal component of velocity, which is 15 cos 40, which is equal to 1.74 seconds. Okay, now in the vertical direction, let's go to green for the vertical direction. I'm going to say upwards is positive, and I'm going to write down SU that. Now, we don't know what height it gets to after this time. That's the unknown thing, but we want to see how that compares to the 3 meters. Initially in the vertical direction, it starts out at 15 sine 40 meters per second. We know at some point it's going to get to 0, but we don't. Also, we know at some point it's going to get to that. We know the acceleration is minus 9.81, and also we know that the time is 1.74 seconds, which is what we worked out over there. So we can then use S equals ut plus a half at squared to find out the height after 1.74 seconds. So the height it gets to is going to be equal to 15 sine 40 times 1.74 plus a half times minus 9.81 times 1.74 squared. Okay, so quite a long equation there. So again, this is lots of work for 1 mark. So I would say then that's 0.5 times 9.81 times 1.74 squared. And then we're going to do 15 times sine 40 times 1.754 minus the answer, oh. That's given me a negative number. Have I done something wrong? So let me try that again. 15 times sine 40 is at velocity, and it's moving at that for 1.74 seconds. We're going to take away 0.5 times 9.81 times 1.74 squared. Okay, 1.92. So basically, the height that it gets to is 1.92 meters, and therefore the answer for this is, well, it's not that one, it's not that one, it doesn't hit the crossbar, the ball falls short of the posts. That's not true either, is it? Yeah. Yeah. Can I do a collab with Science Shorts? Yeah, I'm very happy. Science Shorts, I think, only lives about an hour away from where I live. So Science Shorts, if you're watching, come on down. It'd be great to do some questions together. Yeah, so basically the answer says D, but it falls short of the bar, because I guess if you're looking at this thing, these are the posts which are vertical, and you've got a horizontal bar. So the height of the goal post are 3 meters. I say they're calling that a post. I say that's a bar. So I think, the answer, the most correct one is D. So the ball falls short of the posts because it goes underneath the bar. Okay, so it falls short of the crossbar. Yeah, I did some stuff with Z physics. Yeah, have people not seen these? I did a video that came out last weekend where I said I predict this will come up, and that was a video with Z physics. Yeah, that was a lot of work for 1 mark. Okay. Right, a block on a rough horizontal surface is being pulled by a rope at 30 degrees to the horizontal. We've got mass, tension. What is the frictional force exerted on the block? So, let's think. We've got... Okay, what would be my approach? So the force is going to be equal to its mass times acceleration. So the resultant force is equal to this mass times acceleration, and that resultant force is if I just put on the frictional force here, so FF. That's what we're trying to find. So basically the tension is 100. That angle is 30 degrees as it says there. So the tension times cos 30 minus the frictional force is equal to the mass of this, which is 100. The mass is 20 times this acceleration. So 100 cos 30 minus 20 times 2 is going to be equal to my frictional force, which is kind of what I've done there. So basically the frictional force, add it to that side, take away MA from that. So 100 cos 30 take away 40 is equal to 46.6 newtons, and therefore the answer would be B, would be my answer, because it has to be really 47. Yeah, there we go, that'd be my answer to that. Okay, anything else in the chat? We've got Divya, 47B, excellent. B says coding with Ronak. No, it's C, says somebody who's incorrect. Yeah, there we go. These questions just go on and on and on and on. I don't know how long I've been doing this stream for at the moment, but it feels like forever. Am I forgetting to resolve upwards? I didn't. Okay, it does say here in the question it's accelerating horizontally. So they've got the same thing. Yeah, so basically, because there's... What this doesn't include, I guess, is maybe some like all the forces like normal contact. Yeah, yeah. So basically, it says it's accelerating horizontally, so there must be a resultant force to the right. Okay, right. So the engine of a 1,000 kilogram car produces an output force over time. If the car starts from rest, determine its final velocity once the engine force reaches 0. So the force increases, stays the same, and then decreases. So effectively the area under here is going to be equal to the impulse, because that's the force times the change in time. So that's the impulse, and that's going to be equal to the change in momentum of that vehicle. So just using Newton's second law. So we would then look at the area. So the area, and if you've got something like this, my top tip is to highlight what's on the axes, because sometimes they give you time in milliseconds or force in kilonewtons. So always highlight that so you know what it's got. The area is going to be that area, which is going to be 150 the height times the average of the two sides, which is 10 plus, what's that? That's 22.5 divided by 2. And so the area is 2437.5 Newton seconds. Okay, and that's going to be equal to the change in momentum. If the car starts from rest, then the change in momentum is equal to its mass times the change in velocity. So that's 12. So basically, then the change in velocity is equal to this impulse, 2437.5, divided by the mass, which equals 2.03. Oh, it's 1,000 kilograms, not 1,200. Sorry. I'm going to people say that in the chat. Yeah, so it's divided by 1,000. So that's going to be 2.438. So 2.4 is going to be this one here. So the answer is A. Okay, so I messed that up. Right. Right. Yes, I know I'm making mistakes. Occasionally, even experts make mistakes. And it's not, I don't know the physics, I just didn't read the question properly. Right. So this one's actually one of the few questions on this paper about ratios. So a steel wire of length L and diameter D has a force of, okay, second diameter 2D and length 2. Okay, so I would say start with the diagram. So the first one, we've got a wire of a certain length L. So this is L, and that's going to be D. it's got a force to produce an extension. So we've applied a force to it, and we've got an extension of E from its original length. That's my first thing. We then have a second steel wire with a diameter of 2d, so that's now 2d, a length of 2l, so that's 2l, and it's stretched to the same extension, so E is that thing there, so it's got the same extension as this. What force has been applied to this? So for this question, we know that the two materials have the same Young modulus. So basically, I might need to go to, again, another bit of paper. So the Young modulus, E, is equal to the stress divided by the strain, which equals the force over the area divided by the extension over the original length, which equals FL over EA. Okay, so that is how you calculate the Young modulus. Okay, and by the way, you don't need to do any calculations, but that's fine. So basically, the Young modulus is equal to the force times the length over the extension times the area, but the area is equal to pi d squared over 4. So we can also really say then that the Young modulus is equal to 4 times the force times the length over the extension times pi times d squared. Okay, so that Young modulus will be the same for both, and therefore we can say for the first wire that I've got over here, we can say that 4 times the force times the length divided by the extension times pi times d squared, so that's going to be for the first one in green, that must be equal to 4 times the new force, which I'm going to call, what should we call it, force 2. 4 times force 2, the length is now 2l, we've got the same extension, the same pi, but now we've got 2d, so that's going to be equal to 4d squared. Okay, so we've got this, and we can now start. You can basically now cancel an L, cancel an E, cancel a d squared, cancel a pi, and what we can then say is that 4 times the original force is equal to, we've got 4 times 2 divided by 4, which is equal to 2 times the new force. And so that means the new force, F2, is equal to the original force, F, divided by 2. Is that right? So the answer for this, so that means the new force I've made a mistake somewhere, haven't I? It will be 2F. Okay, that can't be right. What have I done? So the new force is going to be pi d squared over 4, so 4 pi. We've got a bigger diameter, so we'd have a smaller area. Oh, have I messed up somewhere? Just divide the wrong way round. Just the last step. So yeah, oh yeah, sorry, that's what I did. I was almost there. So basically, if you divide both sides by 2, then we can say that 2F is equal to the new force, and therefore that's why the answer is C, which is 2F. Okay? Yeah, the 4 should be on the bottom. Yeah, that's all I did. So it's 2 over 4. It's very, I was basically just putting somebody in timeout on the channel for like their comments. So yeah, nice. There we go. So this one here, basically, in order to get something which has got double the diameter and 4 times the area, but twice the length, means we just need to double the force. Okay, right. Let's just put somebody in timeout in the chat. Basically, I'm not teaching at the moment. With you lot, I guess. I've been teaching this morning with a real class of people, with some year 13s I had doing questions, but because I don't have to deal with any kind of stuff, basically if people do stuff then people will just be put in timeout, or I'll just block you on the channel, but it's all fine. Right, this question here was identical to an AS question that somebody emailed me about the other day, and the key thing is that you've got to redraw this in a much more usable format. What's the resistance between X and Y? So we've got a resistor between X and Y, okay? So that's one way that the current could go. The other way it could go is down here and up here, or down here and up there. So that's like basically when it goes down here, that's like it goes through another resistor, and then it can go either this way or that way. So that's basically drawing the circuit like this. Okay, so we've got point X over here and point Y. So what I've done is basically that it can go this way, which is through one resistor, or it can go through this resistor and then either up through this resistor or through that resistor. So that's the circuit. Now, of course, if you've got two resistors in parallel, both of them are 4 ohms, that's the same as having one 2 ohm resistor. And now we've got a 2 ohm resistor in series with a 4 ohm resistor. So that's an equivalent of basically saying this loop here is 6 ohms, and this bit up here is 4 ohms. And now we want to calculate the total resistance, and the total resistance of a parallel loop is equal to R1 R2 over R1 plus R2. So that's a way of looking at product over sum for resistors in parallel. So here we've got 4 and 6, so 4 times 6 is 24. Divide that by 4 plus 6, which is 10, and that's equal to 2.4. So here the answer is 2.4 ohms is the equivalent resistance, which is A. Okay, is that all right? Cool. Right, there we go. Right, a 12 volt battery is connected to a 100 ohm resistor. To be honest, if you've got a voltmeter, an ideal voltmeter is going to have an infinite resistance. So adding a resistor to an infinite resistance doesn't really do anything. We've got a diode with an operating voltage of 0.6 volts, as shown. What is the correct reading on both the ammeter and the voltmeter? So I would say that this is the same as having a circuit where you've basically got an ammeter in series with a diode, and you'd basically have, because effectively that's got no resistance, this is like having a voltmeter going across that thing there. So the voltmeter, so the 12 volt battery, so that's going to be 12 volts, so the voltmeter should be reading 12 volts, and the ammeter should be reading whatever the current is in that circuit. But if you've got it going from here to here, that diode is stopping it, so the ammeter is going to be reading 0 amps. So I would say the answer for this is D. What do you reckon? So D is what people are saying, and the answer is, oh, they do have D here. So it says here that the loop takes a full share of the current. That's not true, because there's going to be no current going through the voltmeter, so that statement is incorrect actually. So there's no current here because we've got an infinite resistance through that voltmeter, and therefore that's not a correct statement, but they have got the right answer. So we've got 0 amps on the ammeter because there's no current because of the diode, and the voltmeter would be reading 12 volts because it's the same as the PD, the terminal PD across that thing. Okay, yeah. I think it's just one of the comments you put in, that's all. Okay, I love having you here, I just don't want any like other kind of comments which aren't so suitable. Right, here we've got this question. A 12 volt battery is connected, so if it's a circuit thing, put in the numbers. So we've got 12 volt battery, we've got a fixed 100 ohm resistor, and a variable resistor with a range of 0 to 100, so that's 0 to 100. What are the maximum and minimum values of the PD as the contact moves from X to Y? So basically, the maximum reading, if we think about, we've got two resistors like this, and we put the voltmeter across the two of them. If that's a 12 volt power supply, the maximum reading is going to be 12 volts. Okay, so the max, it's not 6, and it doesn't change, so it must be B or C, so I'm going to get rid of the wrong answers. Okay, the other scenario that we have is where you've got the two resistors, and that's 12, like this, and you're basically looking at the potential difference just across. If that's in the bottom position, it's just this. Now, of course, if that's R and that's R, which is the same for them both, and if that's a 12 volt supply, then this value here must be 6 volts. So the minimum is going to be 6. So this is the right answer. Okay, because we've got the 12 volt split between the two things, and when this sliding contact's at the bottom position, it's going to be looking at the PD across this. Okay, right. So yes, it is kind of a potential divider circuit. Number 30, a theme park cart performs a loop-the-loop on a circular track. What is the correct expression for the minimum velocity required for the cart? What is the correct expression for the minimum velocity required when the cart is upside down at the top of the loop for it to complete the circle? So at this top position here, if we think about the minimum velocity, this is where the centripetal force in F, which is equal to mv squared over r, this centripetal force is going to be provided by the weight acting down, which equals mg, and this is where there's going to be no contact force between the wheels and the top of this. So we can equate the two things together to say that this weight, force down, is providing the centripetal force. I'm hoping I'm getting these questions right. I haven't actually looked through them all. And therefore, the minimum velocity v, well, it says basically g is equal to v squared over r. So v is going to be the square root of gr, which is b. Is that the right answer? B says coding with Ronak. Locke says B. Good. Yeah, there we go. So B is the right answer. I think the mark scheme has got that as well. Yeah, that's right, but I guess R is going to be 0, which they've got there, so yeah, they've got the right answer. Good. Right. The next question, 31. Is this the last question? Here we go. A 400 kilogram motorcycle and rider are moving at 15 meters per second around a banked curve with a radius of 60 meters. The road is frictionless. So basically, if we look at this, we've got that person on a banked track. So I'm just going to do this. So there's a banked track. There's going to be a weight force acting down. Which is okay, so we've got a weight force acting down, and there's going to be a normal contact force. Let's just call that F, which is acting at 90 degrees to that surface. What should the banking angle of the curve be for the motorcycle to stay in contact without relying on friction? So this is basically like the limiting case where if they're going a bit slower, there's going to be friction acting up the slope, and if they're going too fast, the friction is acting down. So what we can say is if we've got an angle here of theta, then this angle here is equal to, well, that's going to be 90 minus theta, so that angle there is theta. Or we could say that if that's theta, let me think, so that's theta, so that's theta up there as well. So if we think about the vertical component of the normal contact force, then basically F cos theta is equal to the weight force down, which is equal to mg. Okay, and if we think about, so this is like thinking about the forces vertically, and horizontally, there's going to be F sine theta is going to be equal to mv squared over r. Okay, so I think that's the approach. So basically we're looking at the forces vertically or the forces horizontally, and therefore there's going to be a resultant force inwards due to this normal contact force, but in the vertical direction there's going to be no resultant force up or down. So we want to find the angle theta. So let's say then that from this equation up here, we can say that F is equal to mg over cos theta. And then we can put this into this thing up here to say that F, which is mg over cos theta times sine theta, is equal to mv squared over r. Now that's looking a little bit messy, so we can cancel the m's and we can bring the g down here, and then we've got sine over cos, and sine over cos is just tan, so you've got tan theta, which is sine over cos, is equal to v squared over gr. And then we can put the numbers in, so we've got 15 meters per second, we've got 9.81, and the radius is 60. So that's going to be equal to 15 squared divided by 9.81 times 60, which is 0.38, so inverse tan of that is 20.9. So all of the time we work out the answer first, and then we see which one it's closest to, and I would say the answer is D. Okay, yeah, there we go. Lots of people getting the right answer, I think. Yeah, and I guess basically that's what they did, but it's maybe a bit unclear to see that. So that was my approach for that last question there. So basically drawing a diagram, equating the upwards component of the normal contact force to the weight, and then looking at the resultant force, which is providing the centripetal force, which is F sine theta. And of course, if you've got sine over cos, that's tan. So tan theta is v squared over gr, which gives theta equal to 20.9. Okay, yeah, there we go. Even though it's a multiple choice question, just stick with your trusted way of actually working things out. So yeah, basically that was my work set of solutions, which I was doing on site. So I apologise, I made a few little mistakes. We've got no idea about the grade boundaries because this paper wasn't sat by lots of students, so therefore it's difficult to know what students would have got if they did that in an exam thing. The only one I couldn't do was this question here, looking at where you're charging up a battery where you've got two things across this, and I couldn't work out the answer because I hate these questions. So I would say fingers crossed that doesn't come up. But yeah, those were basically my answers. If anybody liked this, then don't forget you can come, of course, come into my masterclasses this weekend. Book them as soon as you possibly can. They might fill up. If you can't get into the one tomorrow on Saturday morning for AQA, I'm doing the same thing again Sunday morning, and I'll try and do some stuff next week if people really want that. So yeah, I'm afraid I can't go through the full 2024 paper on YouTube, but I will be able to go through some 2024 questions within my masterclasses on the weekend if you want me to do some of those. But yeah, thank you everybody for watching. Hopefully there is somebody watching this, but it's been great to see so many people in the chat. People like coding, people like DVR, so many people out there kind of putting stuff in, and it's great to have so many people here. If you haven't done so already, make sure you subscribe on YouTube, go to my website, A-Level Physics Online, and over the next month, that can be one of the main places you go to find things. The last thing I just want to say is if you go to A-Level Physics Online, go to the main page, go to the past paper finder, and if you go here, you can find all the past papers you need. You can easily select your exam board, if it's A-level, which paper it might be, and you can see I've got video work-throughs as well. And if you click on one of these, it then takes you to my video work-throughs for lots of the past papers for 2023 and 2023, 2022 and 2020, which is like the odd one out there. But yeah, thank you so much everybody. Hopefully your revision's going well, and I'll see all of you soon. Thanks so much.